Hi everyone, welcome to Layman's Learning. Today I'm going to be talking about Chapter 1 of Thermodynamics. This is basically going to be a rough introduction to what general thermodynamics is all about, and I'll also talk about some of the important fundamental equations that we will be seeing in later chapters. So I'd first like to talk about the definition of thermodynamics. We are basically studying the transfer of energy forms. For example, when you look at the combustion process for coal power plants, we start with chemical potential, say from your coal, to thermal, to mechanical, and then finally to produce electricity. This same concept can basically be applied in heat cycles, which will be talked about later on in Chapter 4. So next I'm just going to be talking about a lot about the terms and some of the definitions that we have. So first of all, I'd like to talk about what a system is. We define a system to be material that we have within a defined space. You can have an open system or a closed system. And in open systems, matter is allowed to flow in and out through the system boundary. So now you might be wondering what a boundary is. And if you look closer at this drawing right here, the gray dots that I have, they're basically the boundary. And all of your matter, they are able to flow in and flow out freely. So you do not have mass conservation, which will be important in later chapters. You could also have a closed system where all of the material remains inside the system and you have a fixed amount, fixed mass. So the initial mass is going to be equal to the final mass. So boundary is the perimeter of a system separating the surrounding from the system. And you have two forms of boundaries. First, you can have one that is movable. So that could mean that your system's volume is allowed to change through a moving boundary. A specific example would be the bike pump that is holding gas. And when you're heating it, when you're adding Q to the system, the boundary, which is this lid, is able to move up. Or when you cool it, when you take heat out of the system, the lid is able to go down. And so when you heat it up, the gas basically does boundary work and pushes up on the piston or on the lid. And when you take heat out of the system, the gas contracts and basically the lid will fall. So the second form of boundary is closed. This is basically when your system's volume is fixed. In a lot of questions or problem sets, they would define this as a rigid boundary because basically you don't have this piston that is able to move freely. It's rigid. It's also called isovolumetric, which is a fancy term that we will talk about later. And then heat, which is defined as Q in thermodynamics. Heat is basically the energy that is being transferred from a system to another system that crosses a boundary. And this can only exist through a temperature difference between two systems, or even more systems. Or it could be system versus the surrounding. And heat is very important to know that heat is not the same as hot. Temperature is the measure of how hot an object or system gets. And it's basically a measurement in Celsius, Kelvin, etc. And as I've said, heat is different from hot. Heat is the transfer of energy, whereas hot is basically a measure of temperature. So on this next section, we're going to be talking about types of thermodynamics processes. So what is a process? Process is the act of changing a system's state or configuration by changing their thermodynamic properties. So that's a lot of words that we're dealing with. But basically, we're going to be changing the temperature or the pressure or the volume or the internal energy of your system through different processes like heating, cooling, compressing, or expanding. So here that I've highlighted, all the things that I've numbered and highlighted in pink, they're all major processes that we will deal with in thermodynamics. So the first is isovolumetric, which I've briefly mentioned before. This process allows for the system's volume to remain constant. It occurs when the container has a rigid boundary, and so no boundary work is allowed to happen. For example, the gas within a rigid container does not expand when it's being heated. So when you add heat to the container, the gas is not able to do any work because the container is rigid and you don't have a movable boundary. So basically, no boundary work can be done by the gas. The second process is isothermal, where the temperature of the system remains constant. For example, the latent heat when you have a phase change. So the process of boiling water, where you go from liquid to gas, all of the thermal energy that you add to your system goes into overcoming all of your IMF, your intermolecular forces, which basically help convert liquid water to gaseous H2O. It does that instead of increasing the temperature. And we know that temperature is basically the average kinetic energy of your molecules. So when it's isothermal, all of the energy is going into overcoming all of your molecular forces instead of increasing the average vibrational energy, also known as temperature, of your system. The third process we have is isobaric, in which the pressure of your system remains constant. For example, when you're heating up a system that is exposed to constant pressure through an external weight placed on the lid, it is being subjected to the same pressure. And the fourth process we have, this is quite unique, it's called adiabatic. It's the process where you have no heat exchange, so Q is equal to 0, between the system and the surroundings. The fifth is a unique subset of an adiabatic process, and we call it isentropic, where the entropy of your system remains constant. We have two conditions for a process to be isentropic. First, it would have to be an adiabatic process and also a reversible one. So this would mean that you can't have anything or any of the energy being lost to irreversible processes. Like, say, friction. No energy loss to irreversible processes like friction. And we'll also talk more about process 4 and 5 in later chapters. So now let's go on to talk about some of the thermodynamic properties. There are 5 fundamental properties that are obtained through measurement. And they are temperature, pressure, volume, entropy, and finally internal energy. And from these 5 fundamental properties, we obtain 3 additional properties that have been derived from the prior 5. And they are enthalpy, the Helmholtz free energy, and the Gibbs free energy. And they are defined in these 3 equations. Enthalpy is equal to the internal energy plus PV. Helmholtz free energy is equal to the internal energy minus T times S. And your Gibbs free energy is equal to H minus T times S. Next, we'll talk about intensive versus extensive properties. Intensive properties are basically expressed in units per mass. And they're also written in small case letters. So for example, if I'm talking about specific internal energy, little u, my units would be kilojoules per kilogram. If I'm talking about specific volume, little v, my units would be meters cubed per kilogram. Specific entropy would be joules per Kelvin, per kilogram. So you just have this per kilogram unit dependence. Extensive properties are expressed without mass dependence and is being written in capital letters. And also, a side note, temperature and pressure are always extensive because they have to be measured and they're not ever related to how much mass you have in your system. Internal energy, big U, just kilojoules. Volume, just m to the power of 3, which is your meter cube. Entropy, which is be joules per Kelvin. And then now we're going to talk about the fundamental differentials of thermodynamics. These are very important in later chapters, and I will talk about them more when we get to, I think, chapter 5. So the first differential equation you need to know is the one for internal energy. du is TdS minus PdV. The second is enthalpy. dH is TdS plus VdP. The third is your Helmholtz free energy. dH is equal to the negative of PdV minus SdT. Gibbs free energy is dG is equal to VdP minus SdT. So these fundamental equations, they do have meaning to them. They're not just random, crazy differential equations without any meaning. And it will make a lot more sense when we get to the later chapters and I bring them up more to contextualize why they look like this. But for now, I'm just introducing them to you, and if you don't get it, if it's not making any sense, that's completely fine. And lastly, we're going to talk about some of the partial derivative properties that we will encounter in thermodynamics. The first is the heat capacities. So if you have a constant volume, your heat capacity is defined as the partial derivative of your internal energy with respect to temperature while you're holding volume constant. When you have constant pressure, your heat capacity is going to be dependent on your partial derivative of enthalpy, H, with respect to temperature. And then finally, you have your coefficient of expansion and coefficient of compressibility. Alpha, which is your coefficient of expansion, is going to be 1 over V times the partial derivative of volume with respect to temperature holding P constant. And then your coefficient of compressibility, beta, is going to be the negative 1 over your specific volume multiplied by basically the same term, but you're switching your differential dependence from T to P, and you're going to be holding temperature constant. So that is it for chapter 1. And if you have any questions, please feel free to comment. I am a student and not a certified teacher or a TA, so I'm also learning with everyone here, but I'll try my best to reply, and thank you for watching.